Lecture 20, Memory, or, as Kurt Cobain would put it, right. Now, in executing an instruction, as we discussed quite a while ago, the CPU fetches instructions from memory, decodes that instruction, and depending on what the instruction is, there may be associated operands. And okay, well, if we need operands, add A and B to produce C, well, we have to go get A and B, so we're going to get them from memory. And then after the operation is completed, we're going to write the result somewhere, most likely, assign the variable C based on the calculation that we just did. So that's another interaction with memory. Everything that we do is going to involve memory, and we're going to be interacting with it quite frequently. Right? A simple instruction like addition potentially results in 4 memory accesses. It could be more than this, it could be less, depending on things we already have on hand. But whatever we do, there's no getting away from the fact that interacting with memory is an essential part of executing any program that we're going to run, basically no matter what it does. And as we've discussed, like CPU, main memory is a resource, and that resource needs to be shared amongst multiple processes. And this doesn't necessarily line up with our experience from writing user-level programs. The way that programs are written, application developers behave as if, 1, main memory is unlimited in size, and number 2, all of main memory is at the program's disposal. We know for sure this cannot be the case. An infinite amount of data storage would require an infinite amount of physical space. Memory space surely is limited to the physical amount of RAM in the machine, which is a function of how much money you spent when purchasing said machine. And for machines which are upgradable, unlike modern-day laptops, how much money you might have been willing to spend on third-party RAM to put in. So why do program developers pretend that memory is both infinite and unshared? Well, here's one theory. Compared to the early days of computing, available memory is huge. In the words of Yoda, size matters not. The Commodore 64, introduced in 1982, which admittedly, at the time of recording is 40 years in the past, had a whopping 64 kilobytes of memory. That's incidentally why it's called the Commodore 64, because it has 64 kilobytes of memory. And a 4-byte 32-bit integer was at that level, a significant fraction of memory. There was thought given to each of those allocations. And application developers were expected to basically scrimp and save to avoid even wasting a little bit of memory. It's partly why languages like C and Java support types like short, even though they don't necessarily seem like they're interesting now. Why waste bytes on something that you're not going to use, right? Doesn't matter. You've probably never used them outside a programming exercise, an exam. There are a couple of system calls that take shorts for arguments or flags or something like that, but it's pretty unlikely. But yeah, those things do exist, and part of their heritage is based on the fact that we used to try to save every bit of memory that we could. But in the meantime, memory is now 816 gigabytes, remembering that 1 gigabyte is 1024 megabytes and 1 megabyte is 1024 kilobytes. And so at this point, if we use 32-bit integers and we waste 1,000 of them, would anyone notice or care, right? We wasted 4,000 bytes. It's a little bit less than 4 kilobytes. And 4 kilobytes in the context of, let's say 16 gigabytes of RAM is a rounding error. So would you notice? Would you care? I mean, I might care when I'm evaluating your work using Valgrind, but would anyone realistically notice or care? Okay, that's to a certain extent kicking the can down the road. As the saying goes, we can use a lot more memory before we're in danger of running out. Running out is still possible, right? Just because we have 16 gigabytes doesn't mean that memory is infinite. And for all the integers and things that we might have, right, we are also frequently storing larger things in memory. So that doesn't really work. The other thing that we haven't solved is this idea of sharing. Memory might be big enough for every process to have its own designated area, but that doesn't work if every developer assumes that memory is unshared. So we haven't exactly figured out why application developers could be oblivious to this particular thing. And the answer, of course, is that the modern operating system is responsible for managing the shared resource of memory. And this was not always the case, and there used to be applications that were responsible for helping you out with this. There were various third-party programs that used to help you do this for the last versions of MS-DOS and Windows 95. There were products, one I was thinking of was a QEMM8, and they had completely misleading claims on the box. They would say things that couldn't possibly be true, like it was doubling your RAM or something. Like that's not how any of this works. But they did have some useful tools where they would actually let you move things around in memory if you wanted. So you could like move things to high memory and low memory to adapt to the fact that like different applications had expectations about high memory and low memory and what have you being available. But you're not here to hear my old war stories about moving parts of Windows functionality into high memory so that TIE Fighter would run, even if it's an excellent game. In fact, it's so excellent, I want you to watch this video. I'll show you a little clip of it here.
The Empire is on the verge of success. Soon, peace and order will be restored throughout the galaxy. Even now, our capable forces, led by Darth Vader, are striking back at the rebel insurgents. The rebels are unprepared for our attack.
Okay. Now, one of the major objectives, we said, of the operating system is to manage this shared memory. And just to be complete, we'll start out with the Bane approach of handle conflict by not handling it. Let your reads and writes choose their own destiny. Batman. The simplest way to manage memory is, of course, not to do it at all. Just leave it up to the application developer or the individual user and say, it's your problem now. And early mainframe computers and what have you, and even personal computers into the 1980s, had no memory management strategy. Programs would just operate directly on memory addresses. We would treat memory as a linear array with addresses starting at 0, and it would go up to the maximum limit of the physical hardware of the machine. The section of memory that was actually program accessible depended a lot on your operating system. Back in these ancient times, you would like boot up your computer with a disk in it that had the operating system, and then you would like load the compiler into memory with a different disk, and then you could actually write some code. And so the section of memory that was actually available for your use depended both on the physical hardware, but also the size of the operating system and the size of the other tools like the compiler that you actually needed. And so to write a program, you needed to know the start and the end address of the different segments of your memory, right? And they were different from machine to machine, making it that much harder to write a program that ran on different computers. And hypothetically, you could ship the thing with instructions that say, okay, here's how to look up your start address for your machine, and you entered that here, and here's how to look up the end address. You enter it there in some file. And those are your configuration files, but like really this is asking a lot of the user. Some of them could do it. Obviously people could not always do that. Okay, and so a program would execute an instruction directly on a memory address. So you want to write 385 into memory location 1024, and it gets the job done. Immediately, though, if you have more than one program, one process running at a time, well, as you may imagine, chaos can reign. If the first program writes to address 1024 and the second program intends to do the same, the second program overwrites the changes of the first program, and it probably results in an error, maybe a crash. Alternatively, there's some sort of like negotiation that needs to go on, right? Where we say, okay, this is your area and this is my area, and if we all stick to our area, then we all get along. First program says, I will use memory locations less than 2048, and the second uses locations above 2048, and if everyone sticks to this agreement, then nothing bad happens. This level of coordination, as you will imagine, gets more and more difficult as more programs are introduced to the system. The more you want to have running concurrently, the more haggling there needs to be about who needs how much memory and where it should go, and potentially changes that need to be made to accommodate other programs. And it's basically impossible if we don't control, as in like have the source code to all of the programs that we want to execute concurrently, because, well, we would need to work around them, and not knowing without some help what memory addresses they're going to access, that's actually going to be really hard. So there is one idea that would make this work, which is that on every process switch, we save the entire contents of memory to disk. We restore the memory contents of whichever process is next to run. And as you will imagine, this is incredibly expensive. Like, we are potentially moving, several megabytes or gigabytes or kilobytes, depending on the size of the system that we're talking about, from memory to disk and back every time. That's very expensive, but it does work. The problem is avoided. Only one process is ever in memory at a time. However, there is one more problem, and that is there is no protection in this situation for the operating system. The operating system itself has to be loaded. The kernel has to go somewhere, and frequently it's, depending on your system, they put at the very beginning of memory, so like low memory addresses, but it could be at the end of memory, the high memory addresses, or some of each, I suppose. If you really like making people's lives difficult, you can definitely do that. But the thing is that like an errant memory access in this case potentially overwrites a part of the operating system in memory. Right, you intended to write some stuff into your array, but oh no, like your pointer was null, and so now you overwrote the first part of the kernel at the start of the operating system because your pointer was null and the kernel was located at the beginning of memory. And maybe this leads to nothing bad. Maybe it leads to a crash. Maybe it leads to corrupting files on disk. That wouldn't be good. So, in ancient history, this problem was solved in the IBM 360 by keeping track of some additional information. The IBM 360 divided memory into 2 kilobyte blocks. The 2048 that I mentioned earlier was not a coincidence, and assigns each of those a 4-bit protection key held in a register on the CPU, and the program status word also contains the 4-bit key. So this is your way of saying, all right, this memory is mine, there are other like it, but this one is mine, and making it easy to tell whose is what, so to speak. And the 360 had some hardware support that would detect as an error any attempt to access memory that had a protection code different from your key. And the operating system was the only one allowed to issue or change the keys, making it, again, more difficult for you to accidentally do the wrong thing. And no program could then interfere with one another or with the operating system, which is generally good. And if we generalize that solution, we end up with two concepts, the base and limit addresses. And they define the start and the end of the program's memory, and every access is limited to, well, somewhere between base and base plus limit address. And it's easy to check what happens if we try to access something outside that area. It's easy to evaluate, is it less than base? Is it greater than base plus limit? If either of those is true, it's an error, reject it, decide to terminate the program or send an error or something like that. So the base and limit variables are often used as registers, so comparison is done via hardware. And so when the CPU issues an address for a memory read or write, we do a comparison against base, and we do a comparison against base and limit. These can be done in parallel. There's no reason why it has to be done sequentially. The little flow chart here is just for how you might do it as a person, but in practice you could easily implement the hardware to check these things in parallel. And if in fact the address is not valid, then trap to the operating system, report it as an error. Otherwise, the access is allowed to go to memory. Okay. The situation that we've discussed is an improvement, but it isn't a complete solution. Let's say that we have two programs, just call them 1 and 2, each of which uses 16 kilobytes of memory. Fine. If we load them into memory in consecutive areas, we have something like this, which is A represents program 0 and B represents program 1 and B represents program 2. And we loaded them into memory so that at address 0, that's this part of program A, and the second program 2 is loaded immediately after it. And you can probably see at once what's wrong. Program 1, represented by A, will work as expected, but program 2 will not. The address that's referenced here in the instruction that's located at 16,384 says jump to 28. 28 is an absolute address, so it's actually saying go to the middle of the first program. So it's going to an add instruction that takes place here as opposed to a comparison instruction where it's supposed to go at address 16,412. The problem is that both of these reference absolute physical locations. Now, the IBM 360 did static relocation, so when a program was being loaded with a base address like 16,384, this constant was added to every program address during the load process. That's kind of slow. As you're loading the program, imagine scanning it and looking for every memory address and then updating the memory address to be whatever it was before plus the base. Okay, if we're able to successfully do that, the program works. But can we successfully do that? Well, the answer is it is hard. You can't just look for numbers, because a command like jump to 28 in sort of a pseudo assembly code has to be relocated, but the 28 in a command like add r1, 28, so we're adding the value 28 to register r1, that's a constant, and we shouldn't change it. So how do we know which of those things is an address and which of those is a constant? I mean, for some things like a jump command, sure, that's fairly easy to figure out, but life is not so easy, right? In a C program, a pointer contains an address, but an address is just a number. Like when you break it down, it's really just an integer. And you can dereference an integer variable, and it would take us to a memory address. Whether it's valid or not is not the point here. And if that sounds hypothetical to you, I actually helped a colleague prove a compiler bug where she was evaluating some students' code and it didn't work as expected. And it's because the students stored the pointers as integers, and then they would do a cast to a pointer and dereference them all in one line. And for whatever reason, the compiler didn't really understand what you were doing, and it didn't generate the correct assembly instructions for what was supposed to happen. And when I ran this like with GCC on a different server, okay, the GCC compiler did not fail to understand what you wanted. The point is, though, that addresses are just numbers, so relocation is extremely difficult because there's no good way to know whether a number is just a number. And in fact, when we're writing a program, unless you're writing it in assembly, which quite honestly I think we sort of rarely do right now, we don't usually refer to memory addresses or memory locations when we mean a variable. Like we give them names, right? That is x is assigned 5, right? That's the code that you would write in your C program or similar. So if we know that a variable x is stored in memory, the question arises, when is that variable assigned a location? There's a few different possibilities, right? And compile time, load time, and execution time are possible answers to that question, right? At compile time, that's the kind of thing we see when we saw there was a jump 28 in the assembly code. If we're certain where the process is going to be loaded into memory, then, well, at compile time, we convert those variables to address locations, and that's what happens in an assembly program and in the ancient MS-DOS com format, like the command.com, which is not a website, but in fact just a historical artifact of Windows. And then there's load time, which is the IBM 360 solution. When the code is loaded into memory, we're going to update all of the addresses, and it requires the compiler to give some hints as to what numbers are intended as addresses and what should be updated when the program is loaded into memory. But the real answer is execution time. And again, I don't think that's surprising to you. I think you probably knew that this was always going to be the answer, because, well, we're going to effectively allocate memory dynamically sometimes, right? So how much do we plan to receive from the remote server? I don't know. We'll make a buffer, and we'll ask, what is the size of the data? And the server will answer, the data is 4 megabytes, and you will say, okay, I will now allocate a buffer of 4 megabytes to hold the data. And the only way you could know that is execution time, right? Never mind, where we're going to allocate stack variables and stuff like that. For that problem where we want to receive a variable amount of data, download an arbitrary PDF or something like that, we don't know. So it has to be execution time. Thing is, if we want that to work, we're going to need some help. And we're going to need some help from the hardware developers.